Thank you.
I see it.
Very good. Okay, well, welcome everyone. Welcome to this special public symposium for Section 4, the Civil and Environmental Engineering section of the National Academy of Engineering. My name is Dave Dzonbach. I'm professor and head of Civil and Environmental Engineering at Carnegie Mellon University, and a member of Section 4. And I'm joined today by John Magnuson, Clemensic and Associates, also a member of Section 4. We've put together this symposium with a number of really outstanding civil and environmental engineers. So we are running the big experiment with levels of greenhouse gases, primary among them carbon dioxide, much greater than pre-industrial levels. Earlier, a few days ago, 414 parts per million. We can compare that to 280 parts per million before industrialization. CO2 has a very long life in the atmosphere, hundreds of years. So we basically are accumulating greenhouse gases. We've been doing so since we started the industrial age. And we have this annual diurnal, this annual cycle of CO2 monitored at Mauna Loa Observatory in Hawaii. And we have a steady march upward with effects on temperature, precipitation, and through that, the infrastructure that we designed for environmental conditions. The fourth National Climate Assessment came out in 2018, and included in that work is a look at impacts, risk, and adaptation. The adaptation challenge is critical to civil and environmental engineering. It's here today. It's expanding in scope. Civil and environmental engineers are also involved with trying to mitigate the effects of climate change through source control, negative emissions. We're going to hear about some of those things today. Our program today is broken into three sections. First, on decarbonization. Then, two speakers on that, and then sequestration. We'll have a couple speakers on that, and adaptation. We'll have several speakers on the adaptation challenge. And after each of these, we'll have time for some focused Q&A, and then at the end, a final Q&A and some closing thoughts from John. So with that, I will turn it over to John to introduce our first group of speakers. John?
Okay, thanks, Dave. Yes, we're going to kick it off with decarbonization. And as the speakers make their presentation on each of these blocks, if you could go ahead and put your questions in the chat. Then we, like Dave just said, we have some time reserved at the end of the segments. And at the very end, we have the free-for-all, any question you want. So our first two speakers are going to be talking on decarbonization. And that's Kate Simonen, who's the Executive Director, Carbon Leadership Forum, Professor and Chair, Department of Architecture at the University of Washington, go Huskies, and Don Davies, President of Magnuson Clemensic Associates. Kate and Don, go ahead.
Great, thank you, John. So I'm really pleased to be here today. I'm kicking us off with a little bit of a call to action, as well as an discussion about what is embodied carbon and how the role of the carbon impact of making building materials falls under the purview of, I'm going to talk specifically civil structural engineers in terms of an opportunity to make a significant difference. So, so to set the stage, here we have a slide of global greenhouse gas emissions, and looking to understand when we look at buildings and infrastructure, where do those come into play? So the blue wedge in the upper right of building operations, that's heating, cooling, and running of buildings. But if we look at the total life cycle of a building, from when the materials are extracted from the earth all the way till their end of life, we touch all sorts of different parts of sectors of this commonly, this is how the IEA represents the data. So we touch the landscape and agriculture as we extract wood and other biological materials to use. Emissions from running trucks and excavating materials, the factories that make the cement, steel, and glass, the chemical emissions that take place, as well as the greenhouse gases that are emitted. So all of these emissions take place up front before we actually start using buildings and infrastructure. And if we look at that big pie, we can see that even just iron and steel production is 8% of total greenhouse gas emissions, and cement and other non-metallic minerals are 7%. So if we just think about the use of iron and steel and cement, the vast majority of those end up in buildings and infrastructure. And if we are looking to shrink that global pie, so that we need to be at 50% reduction in the next 10 years and down to 0 in the next 30. And we think about our role in the as users of those materials, we need to be thinking of a total life cycle carbon emissions, both of operating the buildings and infrastructure and building them to begin with. So at the Carbon Leadership Forum, we're really focused on the material impacts of building, and we're using the term embodied carbon to capture those material impacts. So all the things in yellow here on this chart is where we're focusing. So it's capturing those greenhouse gas emissions, so carbon and other emissions that take place across the life cycle, and really focusing on these upfront emissions, because those two main reasons. One is those take place already. They're things that happen right at the beginning when we're looking at new buildings and infrastructure. But additionally, if we think about how to decarbonize those sectors, there's a long lag to be able to do that. We have existing factories and existing technologies in place. In order to meet global climate goals, we need to be demanding and motivating the production of those lower carbon options that are available today. So life cycle thinking is already used in industry, typically using on financial impacts. So the same general concept of thinking about the life cycle from a holistic perspective follows from an environmental impact perspective. And it is life cycle assessment is effectively environmental accounting over the life cycle of a product or process or building. So when we're looking at how do we approach strategies to reduce embodied carbon or those emissions, one of the key first steps is optimizing the project. So that's like not building a building to begin with, or reusing an existing building, designing a road for a long lifespan. That's the first strategy. Another key strategy is around optimizing systems. So that's using alternative materials, say considering a different facade and enclosure system to use bio-based materials rather than aluminum and glass. But it's also about changing the building shape and using materials efficiently. That's the architect and the engineer collaborating to get a good column grid, to designing a system that uses materials efficiently. And then the last strategy is around that I'm going to talk about is around optimizing procurement. That's where I know I'm going to buy a steel beam, but I want to choose the manufacturer that's providing the lowest carbon steel available. So on a performance aspect, from a structural performance, they perform the same way. But from an emissions perspective, there's a really wide swing in available manufacturing processes today. So available today are tools and policies and resources to allow to optimize embodied carbon. And as we are both looking to, as we're looking to make a difference, one of the key thing is we just need to scale up how we're implementing these policies, and to understand that the total life cycle impact of a building needs to include both embodied and operating impacts. So I wanted to just, so that's my slides. That's my making sure we're all talking about the same thing here. It's just great to be talking to the National Academy of Engineers, and I just wanted to emphasize that the climate challenge I see is really a dynamic and exciting one, but one that challenges the fundamental way that I was taught engineering and actually how we treat projects. We're constantly, so we're taught to minimize risk. and we're taught to minimize risk within the area of our domain expertise. So, and from when I was taught about prescriptive-based design as a student 30 years ago, the profession has moved towards performance-based design, and being more comfortable with uncertainty and probabilistic behavior. That sets us up well for being uncomfortable with the uncertainty that's put forth of the challenge put forward to us. But I don't think we're, as a profession, quite ready in our natural happy place to step out into more uncertainty than we're going to need to do to solve the climate crisis. And so I think that means that professionals today are going to be needing to shift how they practice over the next 10 to 20 to 30 years in ways that they weren't ready to do so. So it means that as we educate, we need to be educating our young professionals to be ready to adapt and to be motivated to take risks in a way that we may not have been training them. And it's surely how I wasn't trained. I was trained to be constrained in my thinking. So I'm really happy to have a chance to talk with you today. I want to hand it over to Dawn Davies, a professional who's working to try and integrate embodied carbon as another performance metric in structural engineering. And I look forward to the rest of the speakers, which are showing a wide range of the approaches that we have to address, and I believe we will. So I meant to bring a book to take today from called The Future We Choose, and so it has a motivating statement that I'm going to paraphrase that is somewhere along the lines: this is the time. We are the people, we know what we need to do. We are the only people that both know how and have the time pressure to need to make the changes that we need. So I'm glad that we're having this session. Don?
Thanks, Kate. So let me move to share. So I took this image of Senator Joe Manchin off of a recent speech he was giving, talking about our $1 trillion infrastructure bill. It's not passed yet. Who knows when it's going to pass? But just to make the point, there is significant dollars, government and private. This is talking about government, but there's significant financial income coming into what we're doing with our aging infrastructure, what we're doing with the built environment and the environment we're going to create for the next generation. And at the same time, as Kate and David were just showing, we have a climate problem. There's significant climate challenges. What we do in the built environment is a significant part of either the problem or the opportunity to get it right, depending on how you look at it. I'm always an optimist and look at the positive side of it. And honestly, there's a lot of really positive things that are starting right now, just starting, but starting in ways that we haven't in the past. But the biggest point here, we as the structural and civil engineering community have an outsized influence on what's going to happen, not just for our current generation, but for the next generation on this topic of climate change. But where do we start? What can we do about it? A place I've spent quite a bit of time here recently is simply on you can't manage what you don't measure. David, you had some really good slides there showing how big our problem is. Our ability to measure where our carbon sources are, what carbon we're putting in the air, and to do something about it, there's a lot of blind spots in our industry. And acting on that first, to me, is where we have to start. Now, the math of life cycle, easy to get into a bunch of rabbit holes, but it's some really simple math. At the end of the day, it's just the material quantities of what we're using to create our buildings and our infrastructure times the carbon footprint of those materials. And today we use something called an environmental product declaration, hopefully a third-party verified environmental product declaration, to be a nutrition label to tell us the carbon footprint of those materials, something we should be asking from our suppliers. and simply just multiplying those together to come up with the carbon footprint of our building. It's simple math. The devil's in the details. Getting the quantities right. Do we even track our quantities and know what's in our projects, or are we just flying blind? And asking for, especially in the procurement stage, double bottom line accounting of what goes into our buildings from those materials. Just by asking the question at the right time, we're finding significant ability to move the market and influence what comes next. So I'm going to go through the different materials, concrete, steel, and timber, and show some examples of what I'm talking about there, where we are seeing progress, how we can measure and use this data to make a difference, and what we're just starting to see now that we are starting to ask questions. So when we talk about concrete, there's a lot of different materials that go into making up the soup. Without question, though, the cement and the cement content and what kind of cement is the biggest part of the conversation. We're now starting to come out with different kinds of cement, type 1L blended cements that have more limestone in it that are reducing our carbon footprint. There's always been the conversation of SCMs or supplementary cementitious materials to replace cement that have similar performance characteristics. We also need to look at one of the ingredients that's the biggest component of concrete, though, is aggregate. By volume, it's one of the biggest materials that goes in. Quality control at the batch plant, quality control of the aggregate makes a significant difference. And what I mean by that, here's a recent example of a Los Angeles project of ours, whereby the single intervention of changing the quality control at the batch plant of the aggregate supply, going to an imported aggregate and a higher quality aggregate, better than what was in the local market, in this case, Los Angeles, we were able to significantly reduce the amount of cement that had to go into the project, still maintain the same strength, but we took the variability, we were taking the uncertainty out of the mix and that tighter bell curve. What did that amount to? We took 24% of the carbon footprint of that building out by the single intervention of changing the rock supply going into the project. And the important part about that, we did it with no cost increase. We did it through a performance-based procurement process, bringing the contractors in, asking them the questions, but simply the place of quality control. And the other thing we did is we asked for environmental product declarations, and we competed the suppliers between who could come up with a better strategy to get us to the lower carbon footprint at the best cost. Now, an example of what these EPDs are creating as they are coming into our market, this is just looking at the Seattle market, which has a fairly robust and rigorous use of EPDs between the ready-mix suppliers in Seattle. Just by asking the question for the data and competing and comparing the suppliers against each other, over the last 2 years, we've seen an 18% reduction across the board. In this case, this is looking at 5,000 PSI concrete in the Seattle market. And there's several things that go behind that have led to this, but this is competing the three top ready-mix suppliers. There's this national free database, EC3, embodied carbon and construction calculator, that this information is being housed in. And so this is just mining the data out of EC3. But asking for disclosure, asking for the information, competing suppliers on this, it's making a market difference in our industries. And we're seeing this in more than just Seattle and other markets across the country. It's part of my optimism that I see, where I think we are starting to make a difference, and there's progress that is coming when we simply ask the questions. Now, this is from Heidelberg Cement. They're also paying attention. They know that they got a PR problem. They know that they need to reduce the CO2 in cement. If we were going to go farther with the use of the material, they're looking at carbon capture and storage in the North Seas, pumping it down into prior reservoirs down in the seabed. Is that permanently stored? Is it accountable? Are we accurately measuring the information? There's a lot of unknown there to be shown, but there's also significant investment in just these type of topics. So talking about steel, what do we see in the steel industry? Where is it going? You know, our steel infrastructure, how we make steel, it is 100-plus-year-old technology. It really has been refined at the edges, but it really hasn't changed a lot. global steel supply, it's similar, but especially in the US, it's really about the source of where's the steel made at the mill. And in the US case, most of this is electric arc furnaces. What's the carbon footprint of that grid? How clean is that grid? And can we clean that up? That's the game. That's the conversation today of how we clean up the steel industry. But it's not going to be too far away where in the steel industry, we're going to be changing the entire process of how we make steel. This is from the website of Boston Metals company, maybe to pay attention to, where they're looking at molten oxide electrolysis, changing how we fundamentally make steel, taking carbon out of the process at the initial foundry. This is their timeline for coming online for new facility. They have some serious backers in our billionaire community backing them for what they're going to do. So I think you will be seeing this and similar technologies coming forth in the not too distant future. Lastly, I want to make a few statements about timber. It's a wonderful triple bottom line solution. It's beautiful to look at. It's low carbon. But we have a lot more infrastructure to build than we're going to be able to solve with just the mass timber industry. And we have to be very careful in the supply chain that we get timber right, because not all timber is the same. The simple carbon neutral designation about what happens above the mill is all the same. We need to dig a little deeper there. But if you really get down to it, we're growing fibers, and we're going to use these fibers in engineered wood products to create things. And I really want to focus on a fiber that can grow in 5 to 7 years instead of 40 to 60 years, looking at bamboo. And you know, the secret of bamboo, it's twice as strong and it's twice as stiff as timber. But what it really comes down to is the roots. A tree spends just as much time growing the root infrastructure below grade to create the plumbing to put water up into the tree to grow the fibers we need than it does for the above grade biomass. When we cut a tree, all of those roots die and have to be regenerated every single time you create a new tree. Bamboo is a grass where the below grade plumbing, when you cut the bamboo off, that root structure stays. In fact, it only gets stronger. That's why it's so hard to kill bamboo when you're growing it in your backyards. It's why it can grow in 5 to 7 years. The fibers that we may choose to use for bio-based engineering products, well, it takes 40 to 60 years to do other. We already are doing fiber optimized components in our building design. If we look at a glulam beam, we already grade and species select what wood fibers go into which layers. Now, the bamboo industry is a tiny market compared to where we are with timber today, but I think as we look at time and we look at future bio-based materials, just remember the term fiber optimized design and where we can go. And so just lastly, I just want to end with a call for National Academy of Engineering leadership. Never is there a time that engineering could be more significant than and lead where industry goes than it does today. With that, I'll turn it over. Thank you.
Okay, thank you, Kate and Don. Lots of food for thought there. I'm looking at the chat and I see a couple of questions. There's a couple of questions that I want to defer till the end. For instance, resilience, which is a really good topic. I think we'll do that at the end after the three other main categories, and also the seismic upgrade and retrofitting, and the whole question of, you know, the lowest carbon building you can build is the one that you can build is the one that you don't build at all. So that's another one towards the end. But in terms of the specific, what we just heard on the decarbonization, Kate, there's a question, you mentioned risks and risk management. And could you expand a little bit on what the risk specifically is and how it could be managed, or how we can encourage engineers to deal with what that risk is?
Thanks, John. That's good. I didn't go into the risk of inaction, which is really where I was going. And I think it's an interesting challenge, because solving the climate crisis is a really fairly complex systematic problem. And yet we each individually have our own specific lanes of action. So, you know, I was talking about the risk of inaction, the risk of the status quo, the risk of doing things the way we've been doing will lead us to a future that we don't want. And yet those are externalized risks from an individual project. So I think so I think we need to broaden our understanding of what risk means. So if I'm going to talk from the perspective of a structural engineer, we're typically, I was trained to worry about the risk of death and loss of life. I was worried about the cost to the owner and construction capabilities. So I was mitigating those risks. Increasingly, our owners are asking us to mitigate climate risks, and that they see that as something that we have included. And then how do we think of our ethical responsibilities that go beyond what we're asked to do? So I guess I don't have a super tight answer to that, except that to acknowledge that it's scary, that it is. So for example, I'll give some examples of risks. Trying a different material solution that you maybe haven't done before, being willing to change your concrete mix design to try something else, to change how you market your services in terms of what you're going to be doing and providing for people, and what you won't do there. Those are some examples.
So I guess we really need trailblazers is what we need to show the way.
John, there's one interesting point I'll add to that comment about risk. I've recently been spending a lot of time with different startups, people that got ideas of new technologies that they want to bring forward. Our system of reviewing, approving, testing new materials, new systems, and bringing them into the market, it is hopelessly antiquated, fractured, broken, inconsistent. It is a labyrinth for someone to try to navigate. How do I bring a new material to market that has potential life safety implications in a building material? It's good that they move slow, but there's significant risk for the investment community to want to step in and help bring these new systems, new ideas forward in the market. One of the places we can help is bring some clarity to process. I don't want to short circuit people doing things to show that they're going to do it right, but it is very, very unclear for someone to know where to start and what to do if they have a new idea and they have a new product they want to bring to market.
So you're talking about the risk, the financial risk of.
There's significant financial risk,
right?
And it's a delay. It delays bringing ideas to the market.
Hi, hello.
Hi, Sabina.
Hi, how are you?
Good. I'm not on campus today, so just calling you.
Oh yeah, no worries.
I think this person.
Sabina, we're all listening to your
I don't
conversation.
like
Sabina, Sabina, good, thank you. So Craig Benson, I see our chair has a question. Why don't you just turn your mic on and go ahead and ask your question? Are you there?
Yeah, I am going to put me on the spot.
Well, you got the nice background logo, so.
No, thank you, John. Yeah, we talk a lot about concrete, steel, asphalts, and other material and infrastructure. Should we be rethinking the materials we use? All the materials we use are very energy intensive, they're emissions intensive. Maybe we ought to be rethinking those from the ground up. Materials that have a lower carbon footprint, lower emissions footprint, that last longer, that are more resilient. That might be kind of, Kate, I think you mentioned this, kind of using a new material that's kind of outside the comfort space. And how can we do that? Can we be developing new materials? What do we need to do to make that happen?
Well, I'll jump in. Don talked a little bit about that, right? With his thinking about how do we bring bamboo into a new material, and what are the barriers to overcome them in terms of testing and requirement. I think big picture, we can step back and say there is tremendous opportunity for innovation in the building materials and assemblies. And there's been a lot of work in terms of developing new materials that haven't quite made it into the mainstream. Some of those can be things like using agricultural residuals. So straw that is, rice straw that can't be eaten by animals and that can be turned into MDF panels. There's a new factory in California that is bringing those on. So that being used in furniture, or the new hydrogen created steel processes, or alternate cementitious materials. And these are each different material and use type has different challenges, ranging from how do you add in a different silo at cement plants to how do you confirm that the bamboo can meet the fire testing requirements? And if the answer is always, it's not worth the risk because this one project can't handle it, we won't get over that hump. So how do we come together and share in that risk of developing new materials, testing different systems, investing in that as a country and as a people, and creating things that can be shared globally? We won't solve this on our own. So having one company in Tucson that makes something really awesome isn't going to solve the problem. We need solutions that work globally.
Thank you. So David Goodyear, I see you have a question. Why don't you turn your mic on too and just go ahead and ask the question? I've had it easier for you to just directly ask the question.
Sure.
David?
Well, I don't know which one you're referring to because I've been typing away, but
I was talking about the life cycle.
In terms of the life cycle costs for transportation, life cycle costs can be a major factor. And of course, now any kind of renewal involves a new carbon footprint or a new carbon expense. So, and with life cycle criteria, which are not very strong in the US, frankly, for transportation, you're talking about something more than the margins. It can be a factor of 2 or 3 or 4 in terms of the life cycle for a major transportation infrastructure, depending on what criteria go in on the front end. So that, in addition to this, the carbon declaration, the criteria for design and life cycle design and durability is pretty important. The other comment I would make about the commercial risk with new materials, which has to be recognized by design professionals, is professional liability using new materials. And proof of concept does take time before you get some code official, particularly a code official, to bless a new material for a safety-related application. There is an unfortunate example of high-strength timber back in New York City for a pedestrian bridge that caused a lot of angst for the designer. The bridge was eventually torn down. It was unfortunate because it was a very novel use of a new material and a very green material that turned brown in a hurry.
Oh.
If I could build on one thing, because I think, David, you're touching on a really, really important topic. And this is actually I think the place that the National Academy of Engineers could really lean into. Better definition of the standard of care of when we're going to bring a new material to the market. What do we require? What do we want to see? So, because right now it's a very uncertain field. If someone has a new product or new material that they want to bring to market, they don't even know where to go and what to do with it. And they get very inconsistent messages from the engineering community of where it can be used or not used and what it's good for and not good for. And you end up with an inconsistent delivery then to the market. If we had a much clearer, better defined set of standards and goals of like, this is the steps, these are the processes to bring a new material to market, it would help a lot with that certainty.
I can imagine that may be an easier problem to solve in the public transportation realm, where you have the Federal Highway Administration and DOTs, rather than as opposed to in your markets where you have an unlimited number of owners who may have maybe not a consensus on what they will accept as performance criteria and building usage and things like that. So there's kind of different challenges depending on which part of the civil engineering realm you're in.
Okay, thank you, Don and Kate. We're watching the clock here. And Don, could you stop your share? So we're going to move on to the next block. And if we didn't get to your question, there's going to be some time at the end. And I mean, there's some related topics that were not exactly decarbonization, but are also important topics that we haven't really addressed here that we could maybe get into some of the end. So anyway, Dave.
Thanks, John. And should have mentioned at the beginning, full bios for all of our speakers are included in the agenda, and Nicole just put the full agenda link into the chat if you'd like to look at that. In the interest of time, we're just giving titles and organizations, and it's a pleasure to introduce Kevin O'Hara, who's the lead with 1T.org, the US chapter of it, connected to American Forests, and this is the 1 Trillion Trees Initiative. Kevin, take it away.
Thanks so much, and appreciate the opportunity to be with you all this afternoon to talk a little bit about something that may not be on all of your radars, but something that I think is critical when we talk about nature-based solutions for solving our climate crisis, and ways that we can help shape that approach. So the Trillion Tree Initiative started in a few years ago by the World Economic Forum as a way to catalyze the work of governments, corporations, the non-NGO community in service of restoring, conserving, restoring, and growing 1 trillion trees by 2030 as part of the UN Decade on Ecosystem Restoration. And the US chapter was the first of hopefully many other chapters that will be launched around the world to help catalyze this work. And our goal again is to bring sectors together around forest conservation, restoration, and growing trees. So here in the States, we estimate that we have about 130 million acres of opportunity to restore forest cover for climate mitigation. Currently, we're capturing about 15% of US GHG emissions. We believe that with smart investments across all different sectors, we have the opportunity to get to about 30% of carbon capture over the coming decades. On top of the carbon benefits, there's tremendous benefits up and down the supply chain. We've heard some allusions to the timber markets from our previous panels. Great example of ways to have that carbon captured within the consumer product industry. And then also jobs on maintenance and on planting and on through forestry, through design, through all these other ways to help on these reforestation opportunities. And then of course the ecosystem and the wildlife benefits of conserving natural areas for recreation, for endangered species, and so on and so on. So this includes both. I think we focus again a lot on our public lands and our private forest lands. This also is something I think inclusive of opportunities that we have in our urban context, where we can, where a lot of cities and a lot of localities are looking at ambitious tree planting, tree canopy goals. And we're looking at through this at American Forest through a new equity lens. We have a new tree equity score that we launched this year. That's a decision-making tool for cities to help plan and prioritize where in their cities they should focus their reforestation efforts. And unsurprisingly for any student of American cities, you can make a direct correlation between tree canopy cover and race and income. So, tremendous opportunity to both reforest our cities, provide cooling benefits around urban heat island effect, air quality benefits, stormwater management benefits, but also tremendous equity benefits. So when we talk about our goals, a lot of the work we're doing is in our rural landscapes, but again, I think the focus of what we can do in our urban communities is critical. So 1T.org US, that we look at our work through I think 3 different ways. One is through a process of soliciting pledges, again from governments, from state governments, from counties, from cities, from corporations, to bring folks into what we are calling the most radically inclusive forest movement ever created. And to bring those folks together through this community of practice, it's going to allow for sort of strange bedfellows to have conversations about what their work at the corporate sector around their corporate social responsibility or their carbon offset work might look like, and pair them with a private sector landholder or a public sector landowner that may be looking for ways to finance forestry related investments. And then the third is to talk about how we are creating a system and a network of ecopreneurs, of folks who are developing new products, new systems, new technologies that allow us to get this movement to scale. So I'll dig in a little bit more about the community of practice, because I think that may be of interest to some of the folks in this conversation about how we organize ourselves. So we've got a stakeholder council that is led by Governor of Wisconsin, some Bank of America, MasterCard, etc. But a lot of the nitty gritty of our work happens in our community of practice working groups on carbon finance, reforestation, and then urban and community forestry. We're also building a policy working group, as the previous speaker mentioned, tremendous opportunities around the federal reconciliation and infrastructure bills for sort of once in a generation investments in all of our infrastructure, and our green infrastructure, as well as our gray infrastructure. So these working groups are where we bring those folks together to have these conversations around where the next generation of forest products are going to come from, where we can do matchmaking between carbon buyers and carbon sellers, and where can we bring together again public, private, nonprofit sectors around creating better tree equity in our cities. So I'll start with, and we also then are creating a resource library and a repository of ways for folks within our sector to connect around the latest and greatest around science, around carbon, again, sequestration, and opportunities there for collaboration and learning. So our pledges are really what have driven our first year of growth. We've got a fairly simple process, and again, we're balancing the need between inclusion and rigor on how we're getting folks into the community. But in our first year, we've had 70 pledges of over 50 billion trees, over $260 million in investment to support conservation and reforestation and tree growth, and the estimate of 11 gigatons of carbon sequestered. And then additionally, other organizations, using data, using new products and technology to help support the work. So here are some of our pledges that have come across so far: Salesforce, REI, MasterCard, some larger Fortune ones, non-government organizations. Arbor Day Foundation is a great partner. The Girl Scouts. And then state and local governments. We secured some major pledges from the state of Washington, the state of Hawaii in the last couple of weeks, and in the neighborhood of hundreds of millions of trees. So, as we like to say, this is a group that includes everyone from government to Girl Scouts and everything in between. So proud of sort of the inclusive nature, and again, where we think this movement has the greatest impact by bringing together those non-traditional folks. So for engineers, you're probably wanting to know why and how and what are, get into the hood and talk about what is pledge look like. And I think, conservation is the best way to sequester carbon, to allow existing forests to remain forested for those carbon benefits, ecosystem benefits. But beyond that, what we want is essentially to let little trees become big trees, to capture the carbon benefits of these of nature's sort of greatest carbon sequestration. So on the restoration and growth, there's a number of different ways, from afforestation on rural land or on mine lands, facilitating national regeneration in burn scars in places that have been affected by wildfire. And then on the supporting action piece, things about nursery development, and for ensuring that there's ample seedlings available for all of our partners who have these ambitious goals to be able to achieve those goals. Again, then forest products, workforce development. So the suite of activities that surround what a sort of national reforestation strategy looks like. And I think over the first year, we've had some success in getting our word out. Our chapter is just over a year old, and we had over 178 million impressions in our chapter launch. Within the last month, we published an op-ed with our CEO, Jad Daly, and Mark Benioff, the CEO of Salesforce, on how the corporate sector can get behind these ambitious goals. And so I think we're seeing a lot of opportunities around growth and the message starting to resonate more in that cross-sectoral place. So I encourage folks as they think about projects of what we can do on again, keeping our forests forested, and then incorporating a green infrastructure into project design to the extent that we can, and really how we can sort of continue this conversation and infuse the expertise of the folks who are, who are helping design the next generation of buildings, who are helping, shape the next generation of how our cities look like, and to have that back and forth with the forestry sector, with the corporate sector, and the public sector. So appreciate the time and the ability to chat with you all, and look forward to answering any questions or providing any additional information about where we're trying to get to.
Thank you, Kevin. Thank you. We'll move to the second part of our sequestration talks, and it's a pleasure to introduce Catherine Peters, the McGee Professor and Chair of the Department of Civil and Environmental Engineering at Princeton University. And Catherine will be talking about engineered underground solutions for greenhouse gas sequestration. Catherine, take it away. Catherine, you're on mute.
Okay.
Very
I'm
good.
sorry about that. I've only been doing this for a couple of years, right? Okay, so today what I want to do is share with you my thoughts about negative emissions technologies that involve the subsurface. And that's why I've titled my presentation, Looking Underground for a Climate Solution. It's well subscribed that to achieve the massive decarbonization that we need between now and the middle of this century, negative emissions technologies are needed. And negative emissions technologies are those that remove carbon from point sources and from the atmosphere and utilize it or sequester it. And sequestering it underground is a promising way of dealing with the vast quantities of carbon that need to be removed from our industries and from our atmosphere. Okay, so. Okay, there we go. So on this slide, I'm sharing with you an image collection that the Department of Energy put together for their Subter initiative a couple of years back. The subsurface environment is a busy place, and while oil and gas has been the way we've thought of subsurface energy resources in the past century, in the 21st century, the subsurface will be a resource for negative emissions of carbon. We will vastly expand the use of the subsurface to positively affect the climate, including sequestration of greenhouse gases. That's depicted here with the word storage. But we can also use the subsurface for production of geothermal energy. We could use it for disposal of nuclear waste. And finally, we can use the subsurface as a battery by storing fluids, heat, and mechanical energy. And I'll have something to say about that in a minute. So in my remaining time, I'll make a comment on a few of these. First, about geologic sequestration, because in my opinion, this will be key to achieving climate goals by 2050. In the past 15 years, renewable energy like wind and solar has progressed faster than anyone had predicted, but fossil fuels still dominate. Currently, 60% of our electric power in the United States come from fossil fuels, and predictions are that this will decrease in the coming decades, but it's estimated that by 2050, it's still going to be about 40% of our electric power production. So a means of taking carbon out of our industries and sequestering it is an essential component. Okay. Okay. So on this slide, I'm focusing on geologic sequestration of carbon dioxide. Technologies do exist to capture carbon from point sources and directly from the air. After the CO2 is captured, it can be injected deep underground, such as 1 kilometer or more, where it can be permanently sequestered. And an example is the Sleipner project in the North Sea, where CO2 has been injected since 1996. Another good example is in Iceland, the CarbFix project, in which CO2 is being injected into basaltic rocks. And then in China has ambitious targets for decarbonization, and they believe that geologic sequestration must be a part of their solution, given that their current energy industry infrastructure is so new. This is a way of bridging to this net zero future. Here in the United States, we have had mixed success with commercial scale projects, but we've had great success with research and demonstration projects, and the Department of Energy has now well-established protocols for operations, monitoring, and risk assessment to prepare for an industry of carbon capture and sequestration. I'll tell you that in my own research, studying geologic carbon sequestration has been a cornerstone of my research for nearly 20 years. And the research question that motivated me at the beginning is, will it leak out? And when I started this research, I thought about the enormous geochemical perturbation that would come from introducing the vast quantities of CO2 underground. And I wondered whether the acid would erode the overlying cap rocks, enabling CO2 to vertically migrate from where it was injected. So my students and I looked at this from many angles over nearly 20 years now, and many papers and many PhD students later, I have concluded that it is highly unlikely for CO2 to leak from the target formation where it was injected in a well-designed injection project. So in my opinion, geologic carbon sequestration is a technology that's ready to go. And what is needed is a stream of captured carbon for injection. Okay, my next slide. I have included this slide because I think it's very important to talk about the fact that there's a lot of room for innovation and potential for using the subsurface environment as a battery. The work I want to feature here is the work of Professor Jeff Balicki, who's at Ohio State. I selected him because he's talking about geologic carbon sequestration, not only in the context of sequestration, but also of using that subsurface CO2 as a cushion gas for energy storage, that is the mechanical energy of pressurizing the fluid. CO2 is highly compressible, even at high pressures. And this is an example of simultaneous carbon sequestration and utilization. So in Jeff's work, they have compared CO2 cushion gas as an energy storage technology, and they've determined that this has enormous capacity and energy discharge potential. So I encourage you to look at his papers for more about that. And then I just have one more slide, and this is again about my own research. I have included this. This is not about geologic carbon sequestration. This is about carbon mineralization, which is a form of both carbon sequestration and utilization. Carbon mineralization, by the way, is the exact same thing as mineral carbonation. They're the same thing, just different people say different things. In carbon mineralization, CO2 reacts with metals and metal oxides to form thermodynamically stable carbonate minerals. And the materials needed for these reactions are alkaline materials. And Fortunately, waste streams from existing industries can provide these alkaline materials. And so already civil and environmental engineers should recognize their role in this, because one of the important things that civil and environmental engineers do is deal with waste streams and the environmental impacts of waste streams. And so this is a kill two birds, or maybe even three birds with one stone kind of approach, where we can think about reacting carbon dioxide with these waste materials and thereby stabilizing them, as well as possibly sequestering the pollutants like heavy metals in these carbonates. It's estimated that the collective waste streams from global industries can provide up to 7 billion tons of alkaline materials that are needed. And for coal ash alone in the United States, it's been estimated that between 40 and 200 million tons of CO2 could be captured globally. So in my opinion, there's a lot of innovative work that could be done in civil and environmental engineering here. I do have this beautiful image on the right side of my slide. In my lab, we're examining these reactions with respect to the ability of carbonate precipitation to take up heavy metal pollutants such as arsenic, copper, and cadmium. What this image is showing is that a synchrotron-based image of nano X-ray CT, meaning tomography. And what's shown here is a beautiful crystal that is a spherical crystal of vaterite calcium carbonate. And the also shown here is a precipitated phase of zinc carbonate. So that's some evidence that carbon mineralization can help us with multiple environmental problems simultaneously. So this is my last slide. I'll just conclude. Let me stop sharing, and I'll just conclude by saying that from my vantage point as chair of civil and environmental engineering department, engineers in this field are really well positioned to lead technological advancements in decarbonization and negative emissions strategies, given our sound understanding of large-scale engineering of infrastructure and earth systems. And I look forward to advancing the entire field of CEE to help the nation and the world to achieve a net zero future. Thank you very much.
Thank you, Catherine, and thank you, Kevin. So we'll have time for a couple of questions here related to sequestration, and some questions have been put into the chat. And let's see, I'll ask Craig Benson, do you want to ask a question about the Houston Carbon Sequestration Hub?
Yeah, Catherine, or perhaps this could go to both. There's initiatives right now like large-scale hubs. The Houston Carbon Sequestration Hub is one that I'm familiar with, which are a collection of industries that are working together to create a large-scale carbon repository and essentially all the infrastructure around it. That would seem to me to work well in a dense urban area, but perhaps not have the broader kind of impact we might need. Is there some trade-off or a priority between large scale sequestration initiatives or more distributed types of approaches?
I would argue that to jumpstart this industry, it would need to be large scale efforts, because they would need to be not in the private sector, but in the public sector, with lots of monitoring and risk assessment and government oversight. Over time, as we become more confident about the reliability of sequestration, then maybe it could be more distributed and private based.
Thank you, Craig and Catherine. So I'm going to aggregate a couple of questions here, one from Prasad Rangajuru and one from Kishore Mehta, and they're asking about the urban environment. Kevin, these are for you. What about the integration of green roof solutions in the Trillion Trees Initiative? And what about hazards that trees pose in the urban environment, especially with windstorms. So, Kevin?
Yeah, both good questions, and I think a lot of growing knowledge in the design communities about. I've worked with landscape architects most significantly, but about right tree, right place, and making sure that species selection is appropriate for all the different risks that you're talking about. So we have sort of a right tree, right place mantra, where we encourage sort of the use of the best species for your different contexts, and also a diversity of species. I think you'll see in a lot of places, Chicago, Minneapolis, other places, the tree canopy cover in urban areas decimated by emerald ash borer or an invasive species or a pest, where in the past we just plant a bunch of ash because they grow well in the urban context. Well, now you then lose your entire canopy in relatively short order. So yeah, I think the green roofs, I think, are a great example of innovative ways to use good design to incorporate sort of the micro cooling effects and sort of in that urban heat island, but also within for energy cost savings for other really great co-benefits, stormwater capture, runoff. Green roofs are an incredible solution. Thanks,
Kevin. Richard Tomasetti asked, who sponsors this research, referring to Catherine's talk. And Department of Energy is the primary sponsor of nearly all research in this area. A related question from Glenn Diger, for carbon sequestration, is the missing link a stream of CO2 or a stream of money to pay for it? And Catherine, maybe you could say something about the cost of carbon capture and storage or sequestration, and research underway to try to lower that cost.
I would say that both the carbon capture and the geologic sequestration are parts of the problem are well understood, in my opinion, and technologies exist for both. This won't happen if there's no financial incentive for it to happen. And so, for example, the Petronova plant in Texas was built with a carbon capture unit, but there wasn't sufficient financial or economic return on capturing that carbon. So after a year and a half, that plant, the carbon capture part of that plant, shut down.
Thank you, Catherine. Okay, and there's Bruce Logan has a question. Bruce has provided a calculation. Maybe you can summarize it quickly for our last question, Bruce.
Yeah, I just wanted to point out that trees have to be a really needed part of the solution, but boy, you need a lot of trees. Fortunately, we have a lot of trees in Pennsylvania, and that makes it work pretty well. But with about 7 acres needed per person for the rate that we're burning up our fossil fuels, that's not going to make it work. But I think the case should be made for biofuels, where studies have shown that you can get a lot of carbon stored in the root system. Modern agriculture has released about 500 gigatons over time into the atmosphere from our lost soils. So let's not give up on those solutions as well.
Thanks, Bruce. Yeah, I think it's an all the above strategy. And so you've just highlighted that. Okay, well, we're going to move on to adaptation. And let me introduce our first speaker here. So it's a pleasure to welcome joining us today, John Andrew, Assistant Deputy Director of the Cal Department of Water Resources. He's going to be talking about large-scale adaptation to rising sea level. And John, take it away.
Thank you, David, and it's a real pleasure to be with you all today. Thank you for the invitation. We are going to, in a very quick time period, we are going to be talking about the Delta today, not the variant, but rather the place in California. This is the subject that actually at my department, we actually have a day or 2 day long course on, and you're going to get it in 10 minutes and I think a dozen slides. So fasten your seatbelt. We're going to move very quickly We are going to end with a couple of adaptations as examples. There are so many adaptations possible. But first I need to tell you about what we're adapting to before I give you the examples of the adaptations. Let me start with a place location for you, for those of you that aren't familiar with California. We're actually talking about the San Francisco estuary here, which is San Francisco Bay to the west, the Sassoon Marsh, and then the subject of the talk today, the Sacramento-San Joaquin River Delta. The Delta, about half the water in California drains through the Delta on average. It's at the confluence of 5 rivers, bounded by the Sassoon Bay on the west. The 2 main rivers are the Sacramento and San Joaquin, which it's named for. The other thing about context is that this is a highly managed system. This great Central Valley here has a number of wonderful rivers, but most of them are dammed once, 2, maybe more than that times over. And the movement of water in this area and through the Delta out to the Pacific is a highly orchestrated maneuver between the federal, state, and a lot of local governments. It's an important place, as the slide says. It's a crossroads of infrastructure, which we're talking about today, not just water, but transportation and energy as well. In terms of water, what we're doing here, the Delta is basically a switching yard, if you will, for water management in California. Most of the good water and the high supply of water comes from the north, from the Sacramento River Basin. And the state and federal governments actually have pumping stations here in the South Delta that then distribute water throughout California to basically everything south of California gets some form of its water from our 2 systems. Some of the problems that we create, though, in doing that is that water is coming through these rivers and sloughs. In some cases, our pumps are powerful enough to actually reverse the direction of the water and rivers, which really confuses the fish, causes water quality and water circulation issues. Just overall, not a great way to move water across this place. I should also note that it's very important for ecosystems, where there's a number of fisheries, endangered species that reside or travel through the Delta. And this is an incredibly important spot on the Pacific Flyway. And certainly last and certainly not least, is it's home to about 500,000 people, either in the Delta or around its periphery. Now let's get into some of the problems. And the first is subsidence. And this basically up in the late 1800s, late 19th century, California started to reclaim the Delta for agriculture, mostly using Chinese labor, as it turns out. Before that, the Delta was pretty much about 2 million acres of, well, the swamp, as my title of my presentation is. And the, basically water and land was keeping up with one another in terms of its level. But then once we started reclaiming and draining the Delta, basically we started getting subsidence, compaction from farming activities, further release of carbon dioxide, which we will get to later in the presentation, actually just wind blowing off soil. And now you have an area of the Delta, the central part of the Delta is actually, no exaggeration, 15, 20, 25 feet below sea level. So really what you have now are not islands, you have a series of bowls. And this is obviously a huge risk and a huge problem. Moving on to some other risks. I know for a group of engineers like us, that title is probably kind of funny, but this is actually a slide we use in stakeholder outreach. And if we go into the Delta and talk to the community there, because an earthquake has actually never happened in the Delta itself, there is some conclusion that it never will in the future. And then don't try to talk to them about climate change, because then the conversation gets even harder. So the earthquake risk is indeed real. There are faults in and near the Delta. And then of course its proximity to the many faults, including the San Andreas and the Hayward in the Bay Area, are of biggest concerns. I should add that the levees, we're not talking about Dutch style levees here. We're talking about local agencies pushing up mud, not engineered, poor foundations, and certainly vulnerable just to any type of risk, much less an earthquake. And we do have climate change, as I mentioned, and as the topic of this seminar symposium today. And I don't think that it really takes an engineering degree to say that, you know, if you've got sea level coming up from the Pacific, you have flooding from the watershed side of the Delta, you have these bowls, subsidence, that this story is probably not going to turn out very well in the end. Right now, there are rising sea levels. We think that, you know, we're probably okay if the levees stay in place. That's a big assumption. You know, at another foot of sea level rise. So probably between now and mid-century, we're mostly concerned about riverine flooding as a bigger risk. Of course, when you talk about the Delta and sea level rise, you can really drop the word rise. The Delta has an issue with sea level, period, because of the islands that have become bowls. And if that wasn't enough, we have good old-fashioned critters who are an issue. Nutria, the one on the left there, these are all rodents of one type or another. I guess none of them are particularly pretty, but Nutria, at least in my opinion, is a particularly ugly rodent. These raise havoc in levee systems around the country, if not the world. And they are now in the Sacramento-San Joaquin Delta, and they are public enemy #1 for my sister agency, the California Department of Fish and Wildlife. Just a quick historical political note, the Delta is not a new dilemma. This has vexed one California governor after another for the past 6 to 7 decades. As you can tell from this slide, I think almost every one of these guys they're quite capable people, aspired to be president. One of them actually did become president, but none of them solved the Delta. Just to give you see what kind of a big issue this is for California, let me close with a couple of solutions. And I have one that is very traditional civil engineering, heavy infrastructure. And then I have one that's more on the natural infrastructure side. So we'll start with the bigger civil engineering, traditional civil engineering approach, which is that to address some of the water supply issues that we have in California. There has been a proposal made to actually by my department, we're the sponsor of this project, to actually tunnel under the Delta. So if you may recall from an earlier slide, I mentioned that how the water moves across the Delta to our pumps in the South Delta for distribution throughout California. By tunneling under the Delta, we would then take ourselves out of the risk of levee failure in the Central Delta, whether that's from earthquakes, from poor maintenance, from nutria. You would also place yourself up higher in the watershed, so you would not be creating reverse flows for the fish. You would be gaining higher water quality, getting away from the salinity intrusion from the Pacific. So a lot of benefits from doing this. A lot of details to be worked out, sizes, intake locations, that's all in flux, will be subject to public review. The last thing I was going to say on this, I've already forgotten. Oh, I know. For those of you that have followed California water management, you may recall a concept called the Peripheral Canal from probably about 40 to 50 years ago. This is essentially the Peripheral Canal, but underground. Let me now close with the natural infrastructure adaptation to a slightly different issue, but related. As it turns out, in the Sacramento-San Joaquin Delta, my department actually owns the 2 westernmost Delta islands, Sherman and Twitchell Islands. And for a long time, we have been, most of these islands are for agriculture. That's why we reclaim the Delta. And we have been, and we do the same thing. We rent it out to farmers to grow crops, but we've also been carving off hundreds of acres actually at this point for experiments on what could we do different. And one thing we could do different would be to actually create wetlands using tules. We could use rice. The idea here is that you flood the land. By doing that, you immediately cut off those carbon emissions I mentioned earlier in the presentation. So you've got a carbon benefit there. If you actually grow tules, you can actually sequester more carbon. Obviously, corn is not great for wildlife, as you can tell, but tules are, and so you create habitat. You can also incrementally reverse the subsidence of these islands / bowl. The water that's drained off the islands is improved in terms of water quality than what came on when you flooded it. And you can imagine that this would be a great recreational opportunity for interpretation, hiking, duck clubs even. So we think that this is potentially the future of these islands as we see them now. You can also think that as it's also the future for maybe farming in the Delta in general, because if you're, say, a farmer and you're growing corn, you sell one crop, the corn. But if you're a farmer and you're growing rice, you can sell rice and you can sell carbon, because we actually have a protocol adopted by the American Carbon Registry for carbon sequestration for these projects. So a lot of multiple benefits, as we like to say, in California water management. With that, I'm wanted to close in honor of the historic Chinese community in the Delta. This is a picture of Lok, one of the rural Chinatowns in the Central Delta. And I thank you so much for letting me be a part of your symposium today.
Thank you, John. And we're going to have questions on adaptation after the three speakers. And as John said, anytime we discuss the Delta, there's no shortage of questions. I see some popping in there already. Okay, let me introduce our next speaker. It's a pleasure to introduce Rick Ludick, alumni distinguished professor and director of the Center for Natural Hazards Resilience, University of North Carolina at Chapel Hill. And Rick, take it away. Rick, I think you're on mute also.
Again, there we go. Well, thank you for the opportunity to talk with you today about a great challenge that confronts the US and many other areas around the world, coastal flooding, and the critical steps that the engineering community and indeed we all need to be pursuing to enable adaptation and thus the long-term sustainability of these areas. And one key point is the problem is upon us now and getting worse due to climate change. So briefly, population growth is just putting more people into the Gulf Coast and even the Southeast Atlantic, and it's been growing steadily over the last couple of decades, and growing at roughly twice the national population growth average. And the people that are coming to the Gulf Coast and the Southeast Atlantic coast in particular are coming right into the harm's way of the strongest storms on Earth, and that is hurricanes. And when this happens, we get flooding, we get extreme water levels, we get flooding. We've seen more than our share of examples of this and pictures of this over the last decade or two. And certainly even for over 4 decades, the distribution of damage from US billion-dollar disasters is dominated by tropical cyclones. One thing we don't often know unless we live in some of these coastal communities is that extreme water levels can actually just mean what happens on high astronomical tides, particularly if they're given a little bit of extra push by lesser meteorological events. We call these high tide flooding, sometimes sunny day flooding, or even nuisance flooding. But the reality is that they're more than a nuisance, as certainly these businesses and homeowners would attest. A recent study by Miyuki Hino et al. Looking at Annapolis, Maryland, shows that it's already impacting visitors' ability to access the historic district there. Again, maybe at the nuisance level now, but with additional sea level rise, additional water levels there, we start to get up into where it's real economic impact. 25% of the time, people won't be able to get to the historic district of Annapolis, Maryland. So from a climate change perspective, the latest IPCC report that just came out a few months ago, or last month, or I guess August, so 2 months ago now, points out that regional sea level change has been the main driver of changes in extreme water levels during the past century, during the 20th century, with high confidence, and will be the main driver of substantial increase in the frequency of extreme events, water levels over the next century. And we'll come back to that, but that's certainly what the climate perspective is. And perhaps even more disconcerting, I guess, or concerning, is sea level responds to greenhouse gas emissions more slowly than the global surface temperature. This slow response leads to long-term committed sea level rise that will continue over the centuries and millennia following the cessation of emissions, high confidence. So we're really setting a process in place over the last century and this century that has incredible inertia to it and we'll be dealing with for coming centuries and millennia. Looking at, again, coming back to just the high tide flooding, if we look on the left-hand side at this blue line, this is just over the last century, historic sea level rise at 98 NOAA gauges around the US, Pacific, Gulf, and East Coast. This is the median value, about 25 centimeters of sea level rise. The bars on the bottom of that are the number of times that there's been high tide flooding at those gauges. This is the median over all 98 gauges. So you see earlier in the century, rarely did this occur, but over the last decade or so, we're looking at 3, 4, 5 times per year per gauge as the median. So we're really seeing the acceleration of sea level rise and the manifestation in high tide flooding. We've watched it to this point. If you look to the left, to the right-hand side of the slide, and particularly the lower right-hand image, the yellow bars are for Norfolk, Virginia, and Norfolk, Virginia is seeing high tide flooding 5 to 10 times a year. But as you look, the red curve is where we're headed. And so in 2050, we're looking at between 100 and 200 times per year in Norfolk, Virginia, seeing high tide flooding. And by the end of the century, virtually every high tide cycle is likely to have high tide flooding associated with it unless we mitigate this in some form or fashion. So that's sea level rise. In terms of the storms that we can expect to encounter, particularly tropical cyclones or hurricanes, the proportion of intense tropical cyclones, average peak wind speeds and the peak wind speeds of the most intensive tropical cyclones will increase. And a greater number of the tropical cyclones will have slower translation speeds and higher rainfall potential. And this is going to impact multiple areas of the world, but the Gulf Coast and the US East Coast can expect to see this. With the warming, heavier precipitation, and with heavier precipitation, a slower moving storm, more opportunity for rain to fall in the coast, and thus compound flooding becomes an issue where you have to deal with both rain and storm surge concurrently. What can we do about this? So, this coastal flood modeling systems become really critical in understanding how these pieces fit together, how the hydrologic forcing, the meteorological forcing, the tides and everything come together to allow you to predict how the oceans will respond, what the water levels will get to, what the flooding is likely to be associated with that. This AdCirc-based system is one that I've been working on here at UNC for several decades with colleagues at other universities and federal agencies like the Corps and NOAA. It's been widely used for forensic studies, event-based forecasting, hazard assessments, and design, particularly by the Corps, of multiple of our infrastructure that's protecting coastal cities like New Orleans and perhaps Galveston and Houston. But it's particularly effective as a tool for looking forward and trying to, again, put these pieces together of what a changing climate is likely to bring our way. And I'd like to point out briefly a study by a colleague at Princeton in Catherine's department, Ning Lin, and her colleagues that looked specifically at how versus how 100-year or 1% water levels are likely to change over the coming century. A little bit different climate change scenario, but from the assessment 5. But if we compare what has happened between 1980 and 2005 versus what's projected to happen at the end of the 21st century, we find that the 1% or 100-year flood levels that have occurred in New England will be, by the end of the century, likely to be occurring annually in New England and the mid-Atlantic areas, and every 1 to 30 years in the South Atlantic and Gulf coasts. And if we try to understand what is causing this sea level rise versus tropical cyclone climatology, and this study again used this modeling system to put these pieces together, they showed very convincingly that sea level rise dominates the situation in New England and the mid-Atlantic states, as the climate change report, the AR6 anticipated. But as you get into the South Atlantic area and the Gulf of Mexico, then the tropical cyclone climatology, the change in those storms, the strengthening of those storms become very important. And so again, it's a multi-pieced process that has to be put together and understood if we're going to get to the point of adaptation. And what my experience has been is discussions of adaptation, let alone implementation of it, is difficult for a variety of reasons. Post-disaster, sometimes we have the benefit of direct evidence of consequences, and there may be some willingness to deal with it. Pre-disaster, it has to be prediction driven. You have to be able to tell people what the impacts are going to be that they're facing to motivate them to deal with the difficult aspects associated with it. And thus, for me, the challenge to the engineering and in fact, the broader community is to make more progress on translating and downscaling climate change prediction information into coastal flood prediction information at the local scales, because that's where adaptation is occurring. It has to include the sea level rise and the change in the meteorological states, including precipitation changes. It has to deal with the higher likelihood, lesser events, as well as the lower likelihood, greater events. And it has to get past just the hazard, but actually get into understanding and describing what the hazard impact, what the impacts are in terms of economic, social vulnerability, and others. And as I pointed out, HENO has done a little bit of this, as are other agencies, the Corps, regional studies, and a couple other groups have made progress. But to me, there's still an enormous challenge, particularly bringing in precipitation and getting compound flooding accounted for in terms of getting us to the ability to actually realistically approach adaptation in the coastal zone. So thank you.
Thank you, Rick. So we've covered the West Coast, the East Coast, and the Gulf of the lower 48. Of course, Alaska has their own challenges with coastal flooding and sea level rise, including moving communities inland at great cost. Civil and environmental engineers are quite involved with that. Hawaii as well. It's a pleasure to introduce our last speaker in the Adaptation Challenge and last speaker of the day, Dr. Mari Tai, project scientist with the National Center for Atmospheric Research. Dr. Tai also chairs the American Society of Civil Engineers Committee on Adaptation to a Changing Climate, where she and her colleagues think about a whole range of issues of the role of civil and environmental engineering and adapting to what we've been discussing here. Mari, take it away.
Well, thank you, everybody. Thank you for the invitation to speak to you today. And I'd just also like to acknowledge the role that the ASCE Committee on Adaptation to a Changing Climate has played in helping me think this through, and that to NCAR for supporting my research, and the fact that NSF supports NCAR. So I just want to start with a quick definition of fragility. Fragility is essentially the antonym of resilience. It is the antonym of resilience. And it is dependent on 4 different factors. Exposure, which, as we've already heard from different speakers, is increasing as more people live in urban environments, in the coastal environment, spend time in traffic jams such as this, live in floodplains. It's plus the sensitivity to increases in extreme events. And it's very much a regional issue. Sea level rise is obviously far less of a concern in the Mountain West where I live. But it's something that will require greater coordination between between our states, so that as we think about power outages such as those that happened in Texas, the backup plans of relying on other states aren't then also going to be subject to the sensitivity to extreme weather events, happening in another state upstream that would be supporting us. And of course, society is increasingly interdependent and the infrastructure is interdependent. And we're dependent on all of those infrastructures working together to support us. You lose one of these critical infrastructure systems, such as transportation or energy, and you have a cascade of failures. And we've seen that again in recent disasters. And then finally, the last component is the adaptive capacity. Flood levees can be an incredible and robust solution to keep the water out when they work. And then when they don't work, they can lead to further cascading disasters. And they lead to lock-in, as we've seen along the Mississippi. Increasing flooding has happened as people have moved to live behind those same flood levees. And this point has been made also that climate risk is a financial risk. The disasters that are increasing are because of the increasing exposure, as well as the increasing frequency of those events. In 2020, NOAA reported 22 billion weather disasters. As of July, there were already 10 this year. So we're looking set to meet or that record number again this year. But as you just heard, that the impact, we tend to focus on those extreme events, and yet actually the nuisance events or the sunny day flooding does lead to a greater cumulative cost over time, not only from the mental and physical health impacts and the costs to businesses, but also subsurface degradations, things like the foundation failures, the saline incursion that led to the tower collapse in Miami. And we took an assessment of the fragility of the US infrastructure systems in a recent report produced by the ASCE. This is very much a snapshot in time. This looks at the whole of the US. It's a qualitative assessment. Obviously, we don't have access to all of the information to support it. But as of now, what we could see is that the energy systems are the most important and the most fragile at the current time in US infrastructure. Roads and highways are pretty close, but a lot more work is being put into making sure that they are less fragile, that they have the adaptive capacity. But if you look at this in 20 years' time, potentially water sources will be the governing and the most fragile system, because we currently work with snowpack-driven water solutions in the West. And that's not going to work that's not going to continue to work with the way that we receive our water now. The ASCE produces an infrastructure report card every 4 years. And the most recent one that was released in March of this year gave the national infrastructure a gauge of -C. And, rightly pointing out that there are thousands of power outages in 1 year alone, billions of gallons of water lost daily, billions of hours of traffic delays due to all sorts of things, from construction and to flooding, to just general problems with not enough road capacity. And yet that grade did not account for climate change and the future problems that are coming, our current lack of resilience to the extreme weather problems, to urban development and growth, or to population growth. And as has been mentioned also before, there is this forthcoming infrastructure bill, which really, as engineers, as we seek to implement that infrastructure bill and the projects that come with it, this is our chance to to address all of these issues, to address adaptation and mitigation and social equity in one place. We don't have to build back in exactly the same way as we have in the past. We could build completely differently. Why not build for the society that we want in 30 years' time? Address the adaptation and the mitigation issue by building different types of infrastructure that serve everyone. We've also seen the capabilities of people to work from home over this last 18 months or so. But one of the issues is that we need to change design mindsets, because at the moment, as engineers, we consider failure to be a dirty word, but it really isn't. It's something that we have to learn to accept, that it is going to happen. And the question is, when will it happen and how badly will it happen? What can we do to design in a different way that will allow that failure to occur and yet still be able to operate without having all of the issues and without loss of life, without loss of business? The pictures on the bottom here are from Boulder. On the left, it's Boulder Creek with a cycle path. It's a tremendous amenity for leisure, for green space, to mitigate the urban heat island effect. On the right, it's during the 2013 floods. It is the floodplain. And it allowed for it allowed for the graceful failure in terms of allowing the water to be where it should be. Designing differently can incorporate all sorts of different options, from very low regret retrofits such as hurricane shutters, or mandating tornado shelters within building codes, which apparently is not across a state mandate across every single state that suffers from tornadoes. But probably the greatest weapon in our arsenal is the nature-based solutions. We could use wetlands to break the force of the surge from those more frequently landfalling hurricanes. That will provide natural habitat. It'll remove critical infrastructure from the floodplains. It'll sequester carbon. But in order to do that, we absolutely have to improve our collaboration within disciplines, between civil and structural engineers, between scientists and engineers, to help inform each other what information scientists need to give the engineers to help them make those designs, but equally what the scientists do and don't know and can't supply at the moment, with policymakers, with economists. And probably the economists and the financial organizations are the biggest stumbling block here. They're the people who've been left out the most frequently, and yet they're the ones that are going to fund the research and the implementation at the end of the day. And we need to include the people who are going to be impacted by it, to have an iterative discussion about what is the risk appetite, what are you prepared to lose, and what would you like to have to happen? Oh, sorry, I skipped the last slide. So my take-home messages really are that fragility is increasing at the moment as each of those components of exposure, sensitivity, interdependency, and low adaptability all increase. And as failure is not a case of if, but when and how badly, we need to start thinking about how to design differently to allow greater flexibility to, in our designs. And this will help us with the uncertainty of climate futures. We don't know what the different scenarios are. And as we look forwards into the future and designing the projects that will be implemented with the infrastructure bill, this is our opportunity really to build differently in a way that will mitigate future emissions, that will become give us the lifestyles we want in 30 years' time, make society resilient, and help us to adapt to future and current climate extremes. And hopefully, I challenge the engineers to accept failure. So thank you very much.
Thank you, Mari. And these three talks were interconnected and complementary in really good ways. A bunch of questions here. I'll ask Sarah Slaughter to unmute and ask her question, and maybe I'll add to that for John Andrew that I think there were 2 tunnels that were discussed for a long time. And now it's down to 1 tunnel, and there's a water supply aspect to that's related to the project that I don't think you spoke much about. And but I'll let Sarah ask her question, and John Andrew will complicate it by throwing that in there too.
Yeah, so I was thinking about your comments about all the seismic risk that is there in the subsidence risk. And so looking at the performance of various subways and other tunnels recently during various disasters, I was wondering, I mean, I'm sure you guys are all considering both the earthquake and the subsidence risk from any tunneling activities, but there's also the risk that you're then posing to everything above ground. And then I was also interested in the great quantity of water that you're talking about transferring, which seems like a very effective dewatering technique for all of the Northern California watersheds, which then pulls out all the groundwater as well as all the surface water. So I was just thinking about, this is a great tie to the other talks in terms of interdependencies. So how do you go about thinking about those interdependencies?
Yeah, thank you. There's a lot there. So let's start with David's complicating introduction. It used to be the twin tunnels, indeed. So if you've heard that, our current governor, when he was inaugurated, said that he was in favor of 1 tunnel and not 2. And so we work for the governor, and that's what we're going to do. The twin tunnels was largely based upon, going back to Mary's talk, redundancy. The idea that you could this is a linear system, and if you had 2 tunnels, you could actually take 1 out of service and perform maintenance or whatever you needed to. So that was the mentality behind twin tunnels, but now it's 1 tunnel. It is, in terms of what we have now, it's not invulnerable, nothing is, but we are certainly in a lot better shape taking the conveyance out of the surface, out through the central delta, and taking it underground. We'll be below the peat soil, which is the issue with the subsidence. The earthquake is, this is being designed to current standards, and so that'll be addressed, again, not invulnerable. And then the issues you mentioned about what happens above the ground, above the tunnel is very much a concern, and is a huge concern, as you might expect, of the people that live in the Delta, who are going to have to put up with the construction of this project and then live with it as long as it is around. And then I think going to maybe the last point, in a very general, sort of simplified manner, we're going to be if we were to build this is not done by any means, it would be the same amount of water that we're actually taking now. So the idea that we're draining Northern California, if people have a problem with us draining Northern California, then you have a problem with our water management system in California right now as it exists and as it's historically operated. So the idea is not that we're going to take more water, we're simply going to take the water higher in the watershed, above the delta, above the levees. It'll be the same amount of water. We'll be able to transfer it in a more reliable way, avoiding a lot of the ecosystem issues, providing more reliability in emergencies. So it's really not an issue of more water. It's the same amount of water taken in a different way.
Thank you both. Jerry Schwartz has a question about interdependencies and several questions related to that. Jerry?
Thank you, David. Enjoyed all of the presentations. I'm concerned about the interdependencies in a lot of ways between, excuse me, the sectors, between transportation, energy, healthcare, water, wastewater. Those are physical things, but also the socioeconomic factors that come in there, the governance between local, state, regional, national governance, and how all of this, as we're looking at adaptation, which I think is at least as critical as mitigation, because I think it's immediate. How do you all look at this whole question of interdependencies? Do you study it at all, or are we stovepiped into our transportation, energy, water, wastewater, civil engineering?
Mary, go ahead.
I think that's a great question. It's something that we really brought up a lot in the reports, in our ASCE reports, that we have to address the interdependency issue, and it does require a much greater collaboration across different organizations. I think probably one of the biggest issues that I see, though, is there's also this cascade down from federal to state to municipal to county to whatever. And at each stage, there are different regulations and rules. Yeah, as you can tell, my engineering background was not in the US. And so I'm more used to having one set of regulations that is imposed on me rather than 50.
We'll let you off the hook a little bit and ask Rick Ludick to give his take on that.
Well, clearly adaptation ultimately becomes a societal issue, and it again tends to oftentimes be local. So you have a lot of stakeholders, and inevitably, if you stovepipe this at the beginning, somewhere along the line, somebody's going to be terribly offended, and probably you won't get to the end point that you need to be at. So, it really has to be a coming together of the pieces. The planning community is hopefully a part of that process. I know through our Resilience Center, we work with planners, and they have resilient scorecard processes that they have this myriad of things to work through that are various plans. So oftentimes recreational plans and economic development plans and hazard mitigation plans and all of these things are in conflict with each other. But ultimately, we've sponsored a lot of work to try to disentangle or come up with processes that help straighten that out. And the engineers have to be there at the table at the same time, because the best plan that isn't, has no real engineering process or prospects to it isn't going to get very far either. So it's clearly a team effort, and one that has to be recognized that way and worked from early in the process.
Thank you, Rick. John Magnuson, I'm going to pivot to turn it to general Q&A, but I'm going to take the prerogative to launch that discussion, if you would. I'm going to ask Lillian Barone to ask her question, then we will apply this to all the speakers today. What can the NAE do? And Lillian, I'll let you pose the question.
Thank you very much, David. Excellent conversation so far. Yes, my question is, what would we think are possible steps the NAE could take as we think about these issues that you've posed today? That could be a hierarchy of steps that you would recommend that we pursue, and that in particular we bring to the broadest engineering community possible, so that we are all talking about these issues in a way that allows us to see interconnections between the economic, social, environmental, engineering professions, and science, of course.
If I may, one suggestion is the education piece. Our new civil engineers and structural engineers are being taught to think in the same way and under the same paradigms that we were taught. And they need to know that there is no such thing as a stationary climate, and that it has to be a collaborative effort. And also they need to have thought of ability to collaborate and communicate with other disciplines. Multidisciplinary is really the way forward. We almost need to go back to the original definition of a civil engineer, where that was more an engineer who covered many disciplines, but was civilian rather than military.
Great comment. Thank you, Mary.
Any of the other speakers want to talk about action and NAE and what should we be doing as NAE? Any other comments from other speakers on that? I think that's a really important question.
Yeah, this is Kevin, and I think picking up on Professor Ty's comments about interdisciplinary and encouraging sort of some deeper dives on natural climate solutions and nature-based solutions. And sort of, we think of trees of one avenue to approach this work, but, you know, we think about mangroves, we think about the importance of mangroves and protecting coastal areas in Florida and around the world. So I encourage you to have, you know, more dialogues with across disciplines around what nature can do for us, for resilience, for adaptation, and on all the fronts. So I think there's so much potential for that cross-pollination.
Okay, Don, I assume that hand up means you want to add on?
Yes, and here, let me get rid of my hand too. You know, picking up a little bit on what Maria had said there, there is tremendous youthful energy right now in this whole climate change sustainability movement. We have a lot of money coming into it. One of the biggest things that's missing with all that youthful energy, though, is they don't have the leadership's management problem-solving skills to know how to harness that energy into a cohesive direction. They don't know where the pitfalls are. There's a lot of wheel spinning and parallel tracks. I think something that NAE can really do is help provide leadership, whether that's teaching or whether that's guidance in many different ways. But it's a time for the senior leaders of our industry to lean in, not to watch what's happening, but actually help guide that energy that's there. I don't know how many times I sit in rooms and I'm 20 years older than anyone else that's there. That's what they need.
Okay, John Andrew.
Thank you, John. I would add to the already good comments. You know, the National Academy is a leading thought leader in our field. So I'm thinking about the triple bottom line and sustainable infrastructure. It strikes me that our sector, our field, our profession actually has always paid attention to the economic bottom line, always will. We've gotten really good, I think, over the last generation or so on the environmental bottom line. Where we really need a lot of work is the social bottom line. I recently had the honor of serving on the Sustainable Infrastructure Standard Committee at ASCE, and that was something that I thought was really troublesome, lacking in you know, how we were going to move forward on that opposed to the other two bottom lines. So whatever the Academy can do, focusing on the social bottom line would be appreciated.
Okay, Rick?
Yeah, I quickly would say I really like Murray's slide that had the three quadrants coming, or three sectors coming together sort of in the middle. I really think there's a strong need for people to be able to translate the science of climate into actions, into actual decisions and design, and certainly not to pigeonhole anybody anywhere, but somebody needs to do that translation, and articulating that need seems like it would be a tremendous role for the Academy. The other aspect of this, which is starting to come more and more into focus, is equity. And what you find as you start to look at many of the programs, even at the federal level, the richer communities are much better positioned to take advantage of those programs than the lesser communities. And so again, an advocacy role, an identification role that the National Academy could certainly play is just to try to help us level the playing field. And oftentimes the communities that need the most help, truthfully, are the ones that have been disadvantaged and placed in some of the worst places to live. And so if there's advocacy that can kind of help re-level the playing field, I think that would be another tremendous mission for the Academy.
Thanks, Rick. Kate?
Well, first off, every individual speaker keeps giving the my going down my list, so I would amplify what everybody else is saying here. And I think I want to highlight on the speed of change that's needed, and therefore education and support needs to happen across all the spectrum of experience, not just in emerging professionals, but also experienced professionals. And I think that then from the academy's perspective and the more senior leadership, there's both to lean in and say that action needs to be taken, but also to step back and recognize that even if you have decades of experience, you don't know the answer any more than others as we move into uncertainty. And so to raise up and empower the next generation of leaders to lead to the change that we need.
Thank you. Catherine.
Yeah, I want to say that one of the things that has always shaped engineering education since the beginning of engineering education is the idea of preparing students for a particular industry. And we can't ignore the fact that an entire industry has emerged in the area of climate change mitigation and adaptation. It's estimated that it's a multi-billion-dollar industry worldwide in the area of climate change management and consulting, climate risk, as well as decarbonization technology companies and carbon capture, for example. So I think that this is really inspiring for us, and we should think about what we teach, how we teach, the textbooks we use, or the textbooks that are needed for us to teach. So I'm really glad that our conversation has touched on education, because I think NAE can do a lot in the way of leadership in this area.
Thank you. So I'm looking at the clock and we're running close to time, and it was great to hear the summary from the speakers, and we could go on for several days here and we're just scratching the surface, but I want to go ahead and close it out and say that both Dave and I, on behalf of the Civil and Environmental Engineering section of the National Academy of Engineering, are so thankful to our speakers, to our 7 speakers. Thank you very much. You've been very, very educating to us. It's really, really good. And so I know that, I mean, we just touched on it, and for the organization of this symposium, we've said, okay, climate, we know it will require several things, including decarbonization, sequestration, adaptation, and many other things. And we look forward to continuing the discussion in another venue. And the one thing I know for sure is that civil engineers will lead the way. So thank you all for attending our symposium.
Thanks, John. Craig.
Thank you.
Thanks, everyone. It's great.
Thank you. Thanks to all our speakers.
Thank you.
Yeah, wonderful.
Thank you.
Bye-bye.
Everyone.
Craig, while you're still here, I want to thank you for enabling this great session, and I'm so glad to be a part of it. So,
Well, thank you. I see this as our role of service and a service to the nation. And there's some discussion of that in our section meeting before this too, about we really need to be focused on service. And if there's an area where NAE can have some real impact, this is one. So yeah, I really appreciate you coming, and the other speakers as well. It was just fantastic.
great. Bruce, I saw your comment.
Yeah.
I think.
I mean, what we're doing is dropping a course on like advanced, water and wastewater treatment from the undergraduate curriculum, and replacing that with a course on energy and climate change. Because in civil engineering, yeah. So in fact, I'm working on the notes as you were speaking, or others getting the course ready. But it's really to have the CE curriculum and in particular environmental engineers to lead this, because
Yeah.
we're the multidisciplinary engineering group. You know, we are the cross into all the different things, and I think we really need to take leadership. I mean, it's in the report that came through, you know, Bill Cooper's report through NAE that environmental engineering really needs to redo the curriculum. But I think we're still, a lot of us are still stuck in trying to teach the same old stuff.
Yeah, and students, they come in enthusiastic and wanting to be innovative, and I think they walk away a little bit depressed because we tell them about all the problems, but we don't really teach them how to apply their engineering skills to solve the problem. So I don't think we're serving our students very well at the moment.
Right. And we didn't even talk about methane today.
Yeah.
And that's, you know, that's a whole nother box.
Yeah. But what an opportunity too, to create a new generation of engineers who make this a priority.
Right.
Yeah.
Yeah.
To me,
I mean, given
that's the
how
way you-
important
yeah.
water is to resiliency, I mean, we're right there.
Yeah. And we do need to make this a priority in the way we go about our business. It can't be something we just do on the side. I mean, the issues are too poignant right now. It's really up to us, I think, and academy members, academics, practitioners, to make this a priority in everything we're doing.
Well, let me just say that if, and I'm not a NAE member, but if NAE puts together some effort or panel to look at the education piece, I'd be happy to be a part of it. So please just keep that in mind.
Yeah, Craig, it would be a great follow-up. And I'm saying that because I have a conflict of interest. I sort of have a conflict. I mean, I just wrote a book on this. It's going to be on
great
climate and emissions.
Oh.
And it could be used, you know, for teaching and CE curricula. And I'm not trying to push the book, but so
No, but maybe this is
recognize my
something-
conflict.
yeah.
But yeah.
Section 4 should, you know, we're trying to find ways that Section 4 can create activities of action as opposed to just having a meeting. But where we're having a discussion today, but, you know, but maybe we have a meeting on that. That's about how should we reshape the curriculum? And what is the kind of guidance we want to provide to the universities to shape that new curriculum to create that real change? And that's exciting.
Yeah, I think it's something that builds nicely on the report for environmental engineering for the 21st century, because a lot of these concepts are embedded in there. It's not quite so directed at climate change, but it would provide a good platform. So having a session, maybe get a couple people from that report and, you know, a couple of other people, and have a nice little panel like this again to talk about what we can do and why we need to do it.
Yeah, let's do it.
I have a presentation that I put together, Catherine and Greg, on why civil engineering needs to teach a course like this. And I could send you that. It's just packed with, you know, what will you learn and how will you use it as sort of a, you know, so what if we learn this? What can we actually do?
Yeah, send me a copy.
Given the advancements we've made because of the pandemic in terms of sharing education, you know, guest lecturing over the internet and all this, we don't have to wait for each of us to develop a course. We can, you know.
I'm getting a message. We need to get off.
We'll take it offline. All right.
But let's have Catherine and Bruce, let's have a conversation about this.
Okay,
separately,
sure.
All right.
Sounds good.
Yeah. So let's do
right,
it. All right. See y'all.
Bye.
Bye-bye.